Okay, perfect. So I want to take a look at this second compound here, and we're going to start by naming this compound as an oxirane. That's what I have written here in red. And remember that oxirane is a three-membered ring that has an oxygen in it. So we have an oxirane right here. So if we want to name that as an oxirane, the oxygen is going to take number 1 in that ring because it has the highest atomic number. Then if I look at these two groups, I have a propyl group on the left and I have an ethyl group on the right. Well, the propyl group should have higher priority because it's longer. And so we're going to number our ring like this: 1, 2, 3, just like that. Okay, so if we look at the groups we have on there, we have a 3 ethyl and a 2 propyl. Well, E comes before P in the alphabet. And so this is going to be some kind of 3 ethyl, 2 propyl oxirane. Now all we have to do is figure out the stereochemistry of the two stereocenters. We'll start with the second the stereocenter with the 2 next to it first. And if we start with that, of course, the oxygen is going to be highest. The oxygen is going to be highest priority. We're also having our hydrogen in the back, which is always nice. This carbon is going to be second highest priority, and the propyl will be third highest priority. So when we go from 1 to 2 to 3, like that, you can see that that is clockwise. And so this compound must be 2R. So it's 2R. And now all we have to do is figure out the stereochemistry at carbon number 3. So let's erase all of this and start over again. And now we're focusing on this stereocenter right here. Again, we have number 1 here. We have a hydrogen coming out in front. And hopefully you remember the rule that when we have the hydrogen not in the back but in the front, that whatever stereochemical configuration we see, we're going to reverse that. Okay, and so this carbon is going to be number 2. The ethyl group will be number 3. We go from 1 to 2 to 3 like this. We're heading counterclockwise, which would be S, but again, we reverse it on account of the hydrogen coming out in front. And so this is also R. So we have 2R, 3R, 3 ethyl, 2 propyl oxirane. Well, let's give it a try and name it as an epoxy or an epoxide. So I'll just write, if we want to name this as an epoxy, what are we going to do? We're going to find the longest carbon chain, and we are going to seek to give the epoxy the lowest possible number. So we'll start here, 1, 2, 3, 4. So it's a 3, 4 epoxy as opposed to a 1, 2, 3, 4, 5. All right, so a 3, 4. There we go, 5, 6, 7. So this is some kind of 3, 4 epoxy heptane. So we'll write that down. It's a 3, 4 epoxy heptane, like that. And the good news in this one is that we've already gone ahead and determined the stereochemistry of both of these stereocenters, but they're at carbons 3 and carbons 4 when we name this as an epoxy. And so this is 3R, 4R, 3, 4 epoxy heptane. I'm going to keep moving on. I have the solution to the last one here on my YouTube channel, so you can take a look at that if you want to. And of course, the solution is found in the solutions manual. But let's switch gears and talk about how we would prepare an epoxide. And the good news is that you've already studied how to prepare an epoxide earlier on in this class, because we used an epoxide to make a transdiol, and I have that shown here. We would take an epoxide and we would treat it with a peroxy acid. So this is called a peroxy acid. Okay, so you take a carboxylic acid and you add an extra oxygen in there, and you get a peroxy acid. And there are 2 common peroxy acids that you're going to see in organic chemistry 3111. So MCPBA is a peroxy acid, right? You see the extra oxygen there, and also peroxyacetic acid. Now, if you're unaware of acetic acid, I can help you out with that. So acetic acid is this acid. It's a 2-carbon carboxylic acid. So this is acetic acid. And I know we haven't studied carboxylic acids in depth yet, but you've probably seen acetic acid around in the class. It's a very commonly used weak acid. It's the major component, or the major acid found in vinegar. Anyhow, so these are very commonly used peroxy acids. So for the peroxy acid here, if you were to write MCPBA, or if you put peroxyacetic acid, either one of those would work. And what you end up with is you form an epoxide. So now you've already learned a way to make an epoxide, earlier on in organic chemistry. What's important is that you understand is that epoxidation of an alkene is a stereospecific process. What does that mean? That means that if you start with a cis or a trans alkene, you're going to end up with a cis, sorry, with your R groups being cis or trans respectively on your oxirane, again, respectively, right? So if you start with a cis alkene, you end up with your R groups being cis on your epoxide. And if you start with a trans alkene, you end up with the R groups being trans to each other. I was looking over the quiz this morning, and I have a question that involves something like this. And instead of writing the product like this, the question, I put the answer as a Hayworth projection. And you should know, if you were to draw this out as a Hayworth projection, you would have the ring coming out towards you like this. You'd have the hydrogens going up like that because they're on the same side. You could have the R groups coming down like this. This would be a Hayworth projection of that. Same thing. Anyhow, it's pretty easy to tell that both of the R groups are on the same side of the ring. It actually makes it a little easier, I think. Anyhow, so again, stereospecific reaction. You need to be fully aware of that. Now, what else can we do with an epoxide? It says here that epoxides are also synthesized from halohydrins. A halohydrin synthesis is something we learned way back in chapter 7. If you take cyclohexene, like I have shown down here, we have an alkene, and we treat that with bromine and water at the same time. First, you form the bromonium ion as an intermediate, and then water comes in as a nucleophile, and you end up with this halohydrin, right? And you have to remember that the hydroxyl and the bromine are trans to each other. So we could even pencil that in here, trans to each other. And there is some serious significance with this, okay? And I'm going to show you what the significance is on the next slide. So we have the hydroxyl and the bromine, okay? They're trans to each other. We can treat that with sodium hydroxide, and we make an epoxide. Now, you can probably guess, and there's not a lot of room here, but you can probably guess that when you treat this with sodium hydroxide, what are you going to form? You're going to form this alkoxide. Okay, and then you've got, I should draw the wedge here. Then you've got a bromine here. Okay, so you've got a nice tasty nucleophile here, and now you have a good electrophile here, a good electrophilic center, right, and a good leaving group. Okay, so you can do what's called an intramolecular SN2. So the SN2 happens all in the same molecule. Let me show you. I have it on this slide here. Okay, so the first step is the proton transfer. Okay, we just deprotonate. All we do is deprotonate that, and we make the alkoxide. Now, again, the oxygen from the oxide in the bromine, they have to be trans to each other, and that is very important. So they must be trans, must be trans in order to do this elimination, or this SN2 is not an elimination, this SN2 reaction. Why is that? Does anybody remember the term for when the oxygen is up like this and the leaving group is down like this? We did look at this earlier on with respect to elimination reactions. That's why I brought that word up when I wasn't supposed to. Can anybody remember what the name of this orientation is? When the oxygen is pointing up and the bromine is pointing down like that?
Axial?
Sorry, what's that?
Axial?
Well, both of the groups are axial, yes, and you're absolutely right. They're both axial. I'm asking what the relationship is between the two, between the nucleophile and the bromine. The word is, there you go, Diego got it. It's antiperiplanar. Okay, so you can see that this group. Let me highlight it. Okay, this group and these bonds are antiperiplanar to each other, okay? And they have to be antiperiplanar in order for that SN2 reaction to occur. Remember, you can draw antiperiplanar like with a sawhorse diagram, right? Like, so if you have, your oxygen like this, and you'd have to have your bromine antiperiplanar. So if you have your two, alkyl groups or alkyl groups like that, right? They have to be in that arrangement in order for this SN2 reaction to occur. Like, for example, and I'm really dogging on this here, but if you had this, okay, so if we had something that looked like this, okay, forgive me, I'm trying my best here with my If the bromine was up here, for example, okay, the SN2, so SN2 will not occur. Okay, won't happen. They've got to be anti-periplanar to each other in order for that SN2 reaction to occur. Also, I just want to, refresh your memory. Intramolecular, what does that mean? That means that the SN2 reaction is happening inside the same molecule, right? An intramolecular reaction. All right. What else? So we've learned two methods to prepare an epoxide, either to use MCPBA or peroxyacetic acid. I'll write that in here too. So we'll put that, or either one. That works, right? And those are things that we learned last semester in Organic Chemistry 1. Or you can do the two-step process, right? You can make a halohydrin in the first step, halohydrin. And then you can do an SN2 in the second step. Remember, anti-periplanar, okay, for the SN2 reaction, the intramolecular SN2. Both of those are perfectly acceptable. And I know you've heard me say this a few times in this class, like, oh, Mr. Dion, why do I have to know 2 ways or 3 ways to do the same thing? Well, it's like I've told you before, all good organic chemists should have, a few ways of doing every reaction under their hat. And the reason why is because, let's say you had a big molecule that had many functional groups in it, and besides your alkene, and you want to make an epoxide. Well, let's say peroxyacetic acid doesn't work for whatever reason, okay? Well, then you got to try something else, okay? That's what research is trying things over and over until you find something that works, and then trying to find an explanation for why it works. Anyhow, identify the reactants that you would use to form a racemic mixture. So we're not really worrying about the stereospecificity here, but it says here that we have to identify reactants. You can see that we have epoxides, right, in all of these. So that means we're going to start with an alkene every single time, right? So let's take a look at the first one, and let's analyze the 4 groups, okay? We have 2 phenols, a methyl, and a hydrogen. Well, I'm going to have some kind of alkene. It's going to have 1, 2, 3, 4 substituents. I'm just going to go out and throw it out there to my students. I've got 2 phenyl groups. We'll start with those. Would those phenyl groups, would they be trans to each other, or will they be cis to each other, do you think? Not a trick question.
Trans.
Absolutely, right? Because they're trans in this molecule, right? The 2 phenyl groups are trans on the ring, and so they must be trans here. So I'll put 1 down here, and I'll put 1 down here. So remember that pH is the same thing as having a phenyl, okay? Like that. Okay, so we got that down. All right. Now what else? I have a methyl group that's going in the back, so I'll put my methyl group up here, and then I have a hydrogen down here. So if I put all of this spinach together, what does it mean? I'm going to take this, and all I'm going to do is I'm going to, let me get the black pen here. I'm going to treat it with, I don't know, I'll try MCPBA. MCPBA. Okay, and that will give me the product that's on the far left. Or if you're feeling cheeky, maybe in the first step you want to make a halohydrin, right? First step, halohydrin formation. Second step, treat it with sodium hydroxide. Either one of those is going to work. Let's give a shot at the next one here. So we've got, we're going to start with an alkene, okay, to make an epoxide. I'm just going to circle 2 groups here. What about this cyclohexyl group and this proton? Based on the ring that you see here, in my alkene, would these 2 groups be cis to each other, or would they be trans to each other? The 2 groups I have circled in blue.
Cis.
Absolutely. They're on the same side here, right? They're both cis here. And so that means I'm going to have a cyclohexyl up here, boom, and I'm going to have a proton in the back. That means I have my methyl down here and my hydrogen down here. The same thing applies from the last reaction.
Mr. Dion?
Yep, go ahead.
For the first one, do we have to draw out the racemic mixture, or just it's assumed? Or?
No, it just says assume that you get a racemic mixture.
Oh, okay.
So you don't have to draw both.
Okay.
Yeah, and the same thing applies here. You would use the same conditions. Either set of conditions works, and you get the product. This one here, I don't think it's really trickier. It's just, here you have, we call this You're like, what? Yeah, we call this spiro when you have a ring attached to one carbon like this. It's a spiro group. Anyhow, so this alkene, I mean, you have this spiro ring coming off, right? So you have the 1, 2, and then you have, right, something like this. Forgive me, my drawing here is a little crooked, but you get the idea. And then on one side, we have the hydrogen, right? And on this side, we have the methyl group. And you might be, don't think like, oh, I could just write anything I want for this one. No, 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 because you've got to be very careful with the placement of that oxygen, right? If we count, we have 1, 2, right? If we count from here, we have 1, 2, 3 before we get to the oxygen. So it's a different number, right, to get to that oxygen. So the oxygen has to be closer to the hydrogen than the methyl group. All right. Well, anyhow, we would do the same thing here. Can I still do paste? Was that weird? Paste. Ooh, there we go. All right. Moving up in the world here, and we would end up with the product. Give me a thumbs up if you follow me on that one. Epoxidation, making an epoxide. Thanks, Sean. Thanks, Kevin. Excellent. Because now we're going to switch gears a little bit. All right. Thanks, Yvonne. Perfect. All right. Good. Great. As they say in Scottish. Let's move on. And I have some good news. We're going to skip the whole section on enantioselective epoxidation. I'm not going to ask you anything about enantioselective epoxidation, so don't even worry about that part at all. I've never asked a question about it in the past, and I'm not going to start now. I taught organic chemistry for chemistry majors before, and I think I asked them a few questions about it, but we don't even look at that in this class, and it's not on the ACS final either. So let's move on. And this is really what I wanted to mention to you guys on Wednesday morning, is that I was like, well, on Friday, we're going to talk about ring opening of epoxides. And I'd say this is the major part of today's lecture, is talking about ring opening of epoxides. It's not, mind-boggling or anything, but you have to understand that there's a couple of different ways that we open epoxides. So it says here, epoxides, if I can find it, come on. There we go. Epoxides are useful synthetic intermediates. Because of their significant ring strain, epoxides are reactive towards weak and strong nucleophiles like a Grignard. So if you have an epoxide, right, they're pretty strained, right? That's a pretty small ring. But a Grignard reagent, think about it. If you had methyl magnesium bromide, well, that's a good nucleophile, right? What if you had a hydride? A hydride, that's a good nucleophile. If you had an alcohol can be a nucleophile under the right conditions. An alkoxide, that could be a nucleophile as well. Excuse me. And an epoxide is electrophilic to some degree because we have a dipole going this way, and we can even render an epoxide even more electrophilic if we treat it with acid. And I'm going to explain that to you over the next few minutes. So first thing is we're talking about just nucleophiles, okay? Strong nucleophiles, not weak nucleophiles, strong nucleophiles. You've got to know the difference between a strong nucleophile and a weak nucleophile. So strong nucleophiles, generally speaking, have a charge, right? Have a negative charge, okay? So we could even write that in here. We'll put here negative charge, okay? Negative charge, like that, and we'll react readily with epoxide. So what would happen if you were to take excuse me, ethylene oxide and treat it with hydroxide, like sodium hydroxide, potassium hydroxide, whatever? You get an SN2 reaction. So you get a nucleophilic attack, and then this step here where the ring pops open, okay, just like a jack-in-the-box, okay, it opens up, okay, and then you're going to add 1, 2 carbons, right? So you have 1, 2 carbons added, and then an oxygen. Then in the next step, you treat it with water, and it gets protonated. Okay, so we had these 1, 2 carbons, and where did they come from? They came from the 2 carbons in the epoxide. And what you're going to see moving forward, and I know you all read this section of the book, is we're going to look at a few syntheses where we add a couple of carbons, all right? Opening of the ring is thermodynamically favored due to the relief of ring strain. So basically you relieve that ring strain. If you take a look at just a regular ether and were to treat it with sodium hydroxide, well, an ether has such a low potential energy that the activation energy is really, really huge. And so that's why you can't just take an ether and hit it with sodium hydroxide and make an alkoxide. Whereas with the cyclic ether, the epoxide, the ring strain is so great that the activation energy is much lower. In fact, the alkoxide is even more stable, right? It has a lower potential energy than the epoxide. And so that is why the ring opening of the epoxide is thermodynamically favored. You got to know why something happens, right? Anyhow, here's a pretty cool slide. It says here that epoxides can be opened by many other strong nucleophiles, okay? Let's take a look at all of these nucleophiles and what the heck you can do with them. The first one, this is an alkoxide. An alkoxide, if we use an alkoxide as a nucleophile, we can make, what's this down here? We have, looky, we have an ether. Okay, so we made an ether there in that one. What else? This nucleophile here, this is sodium cyanide. So this is using cyanide as a nucleophile. Now, when you have the cyano group attached here, it's not called a cyanide. It's now called a nitrile. So we can make a nitrile. And nitrile is one of the functional groups that we took a look at in Organic Chemistry 1. What else? This is called sodium hydrosulfide, NaSH. So this is hydrosulfide, sulfide like that. And if we take hydrosulfide and we hit it with the epoxide, we open that up and we make a thiol. Okay, so the sulfur analog of an alcohol is called a thiol. If we were to use a Grignard, so here's a Grignard, right? A Grignard, we end up just adding an alkyl group. So we add an alkyl group like this. And then here we have LAH, which is lithium aluminum hydride. So this is a hydride. And then we just add a hydrogen, right? Just add a hydrogen like that. Okay, there we go. But what else? It says here that ring opening of an epoxide is also regioselective and stereoselective. And if you're rolling your eyes, don't worry. I'm going to explain the regioselectivity and the stereoselectivity pretty quickly, and it should make good sense to you once you look at the rationale. Well, who am I talking to? You read the book 3 times before you came here. Let's move on. It says here ring opening reaction. So regioselectivity. You got 2 carbons in an epoxide. So what if you have an asymmetrical epoxide like this one right here? You can see this one side has 2 methyl groups. The other one has no methyl groups on it. So let's see here. It says epoxide ring opening is SN2. So the least hindered carbon is going to be more reactive towards a strong nucleophile. Right? If we were to draw the mechanism for what's happening in this reaction, I'll redraw the epoxide so you don't have that green square there. Okay, what's happening is your nucleophile is going to attack the least hindered carbon like that, and it's going to open up the ring like this. Okay, then you're going to end up producing what? You're going to have 2, oops, I'll use my black pen. You're going to have 2 methyl groups. You're going to have the alkoxide like that, right? Then you have the other carbon, right? That's this carbon right here. And then you have your nucleophile attached to it like this. In the next step, right, when you treat it with H2O, that's when you do the proton transfer. Okay, so what's the rule here? If you take an epoxide and you treat it with a strong nucleophile, it's just going to go for what? The less hindered side. So that explains the regioselectivity. What region of the epoxide is getting attacked? All right, now let's talk about the stereoselectivity. If you understand inversion of configuration, and I'm 99.9% sure that all of you do, if you understand inversion of configuration, trust me, it's not that much of a stretch. Here we go. We have a strong nucleophile. We have a beautiful epoxide. We look at the 2 carbons of the epoxide. If you don't see them, I'll help you. Look, we have 1 carbon right here and the other carbon right here of our epoxide. Which one of them is less hindered? Well, it's the one that's got less carbons attached to it, right? Okay, sounds good. And so our nucleophile is going to attack the least hindered of the 2 carbons. And where is it going to, what happens when it attacks? It's going to proceed with inversion of configuration. And you're like, well, what does that mean? Okay, inversion of configuration. Well, look, if this carbon-oxygen bond that I just highlighted in yellow, if this is pointing up like that, that means that the nucleophilic attack is going to come from behind, backside attack, right? Backside attack. So that means it's going to come from the bottom, and that's why it's going to be pointing down like this, okay? So now our nucleophile, when it's bound, is going to be pointing down, okay? This is inversion of configuration, something we learned way back in chapter 6 in this class, okay? So you got to understand inversion of configuration, okay? If you really need to go into detail on it, if you want to look at it in terms of what it looks like in the chair conformation, since this is a cyclohexane ring, and this is not shown in our textbook, and I know you probably don't love it when I talk about things that aren't in the textbook, but let me show you. If you have an inquiring mind, I'll try to draw the epoxide. So you have your 6-membered chair like this. If the epoxide is pointing up like this, right, then you have the methyl group pointing down like this. I'll just put methyl behind the page like this. And you have a hydrogen pointing down like this, right? Remember, the nucleophile is going to attack from the back side. So your nucleophile, right? It's going to attack walla walla bing bang. Boom, from the bottom like that, right? And then you're going to end up with the hydroxyl. I'll skip the alkoxide step. And then you're going to end up with your CHEM looking like this with the hydroxyl pointing up and the nucleophile being down like that, okay? And you have your methyl group like that. Anyhow, I hope maybe that will help you, maybe not, but that's what it would look like in the chair conformation, right? You don't want to throw your chairs out. You spent so much time learning about them last semester. All right, so that was a strong nucleophile, okay? Let's summarize what we just talked about in the last like 6 or 7 minutes, okay? A strong nucleophile is going to attack the least hindered carbon, okay, and proceed with inversion of configuration. So let's put it here. Strong nucleophile. What's going to happen? You're going to get it's going to hit attack at least hindered carbon, and it's going to proceed with inversion of configuration. Okay, that's a strong nucleophile. Okay, now we're shifting. We're changing gears. Okay, that was the first part of ring opening, was just yakking about strong nucleophiles. Now we're going to switch gears, not entirely. We're still going to talk about ring opening, but we're going to talk about what's called acid catalyzed ring opening, okay? So this is something different, and there's a different set of rules here. It's not always going to attack the least hindered carbon. So you got to be able to separate these two things in your mind, okay? Now, this is what I really wanted you to take a look at before coming to class today. These two conditions for ring opening. So it says here, acidic conditions can also be used to open epoxides with a weak nucleophile, okay? What's a weak nucleophile? Water or an alcohol. So weak nucleophiles, I know that it says them here, but water or an alcohol, those are the weak nucleophiles, okay? All right, and what's an acid? Well, HCl or HBr, these are acids, okay? It would also work with sulfuric acid, I suppose. In fact, I think I've done it with sulfuric acid at some point in my life. Anyhow, so what happens, okay? What you're going to do is you're going to take the epoxide and you're going to treat it with an acid. What is the acid going to do? Well, the acid is going to protonate the oxygen, right, and convert this to an even better leaving group, okay? An even better way to think about it is this. If you have a positive charge in this oxygen, what's that going to do? Let me redraw this whole damn thing, okay? And this is covered in another slide. I just can't help myself. Okay, if you have a positive charge in that oxygen, think about it. There's a wicked strong dipole pulling electrons this way. Oxygen is the second most electronegative, element in the periodic table. I know we always think fluorine. It's number 1, right? Well, oxygen's number 2. It's pretty darn electronegative, right? So it's pulling electron density towards itself like crazy. And what it does is it's going to render those carbons even more delta plus, okay? And that's why it renders the ring so susceptible to nucleophilic attack. So after you protonate it, then your nucleophile can come in and you end up, adding 2 carbons. So look, these 1, 2 carbons, 1, 2 carbons are these 1, 2 carbons like this. All right. All righty. Well, let's keep moving along here. It says water or an alcohol can also be used as the nucleophile under acidic conditions. Okay, so it doesn't necessarily have to be, let me back up, make sure I explain everything thoroughly. It doesn't necessarily have to be HX, okay? It doesn't have to be HCl or HBr. It could also be H2SO4, okay? Or any kind of catalytic amount of acid. In fact, when you see H plus, okay, in square brackets, what that means is an acid catalyst. Okay, it's just a catalytic amount of acid. That's all that means. All right, so it says here, water or an alcohol can also be used as the nucleophile under acidic conditions. So you take a catalytic amount of acid, and then you have that stirring with your weak nucleophile. Now, what's the intermediate in both of these cases, right? The first thing that's going to happen is you're going to protonate that ring. If you have water, right, if you do the reaction in water, water's going to come in and attack, okay? Already saw that. If you have an alcohol, the alcohol, right, the oxygen is going to attack like this, okay? What students find challenging sometimes is just thinking about all of these things in terms of the products, okay? And that's the reason why I keep labeling these carbons, 1, 2, 1, 2, is sometimes it's a stretch for students to imagine what's going on here, okay? Antifreeze, ethylene glycol, which I've mentioned earlier on in this course, antifreeze is made industrially by this method. They actually take ethylene oxide and just treat it with sulfuric acid and water, like that. I'm not going to ask you about the industrial synthesis of ethylene glycol, though. I doubt. Here's the whole mechanism, okay? Should you be able to draw this? Well, hell yeah. Heck yeah, right? You should be able to draw a hydronium ion, just like this. You should be able to draw the proton transfer steps, okay? So now you've got your oxonium. You should be able to draw a nucleophilic attack, right? This is not something new, okay? Then you should be able to draw the last proton transfer where water's going to come in. And what else do we get besides our product at the end? We also end up with H3O plus, right? We've got more H3O plus and we're ready to go again, okay? So you have to know this mechanism. All right, that's a song by Rage Against the Machine. Know your mechanism. All right, let's keep moving. It says here, ring-opening reactions of epoxides. Now we're going to talk about the regioselectivity. Okay, so this is something else that you have to be aware of. Okay, so it says here that under acidic conditions, the nucleophilic attack still occurs at the less substituted carbon if you have a primary and a secondary carbon. Okay, now here we have a primary carbon. Why is that a primary carbon? Because it's attached to one carbon, right? The oxygen doesn't count, so that's a primary carbon. Why is this carbon a secondary carbon? It's because it's attached to 2 carbons. Okay, so you understand the difference between primary, secondary, tertiary? Good. Let's do it one more time. Why is this a tertiary carbon? Because it's attached to 1, 2, 3 carbons. Okay, we've established the difference between primary, secondary, and tertiary. If you have primary and secondary, and this is something you've got to be able to do, the nucleophile is going to attack at the least hindered carbon. Done. That's the answer. Okay, it's just going to attack at the least hindered carbon, and you, my friend, are done. If you have a tertiary carbon present, then the nucleophile is going to attack at the tertiary carbon. Say, what? Why would the nucleophile attack at the most hindered carbon? Right? This goes against everything we've learned. You're like, okay? Well, the reason why is because the first reaction that I have shown here, the reason why it attacks at the primary position versus the second is based on sterics. Okay, it's just based on sterics, which is size. Okay, so it's going to go for the least hindered. The second one here is when you have a tertiary carbon, it's not based on sterics, it's based on electronics or electronic effects. And that's what we're going to talk about on the next slide. Okay, why does it attack? Why would it attack at a tertiary carbon? Well, it says since the epoxide is cationic, right? You saw me draw, or you saw me have it in the previous slides. I drew the epoxide, whoops, like this, okay? Something like this, okay? Well, the electronic effects, right, because of the positive charge on that oxygen, what it does is it results in the carbon-oxygen bond to the tertiary carbon being much weaker. Okay, it weakens it, and that's what's being shown here. Okay, you could even write it in here: weaker bond. And why would that be weaker? It's because if you were to stretch that bond out and put more partial positive character on here than here, the delta plus is going to be more comfortable on a tertiary position, right? It's going to be more partially stabilized by hyperconjugation. Okay, so that's the rationale. Okay, that's the answer. That's the man behind the door. Okay, if a tertiary carbon is not present, so if there's no tertiary carbon, it's just sterics. Okay, so the only time you have to invoke this rule here, okay, what I just showed you, is when you have a tertiary carbon. If you don't have that, just to hell with it, just go with sterics. Okay, so if you have a primary and a secondary, you're going to go for the primary because it's less hindered. If you have a secondary and a tertiary, it's not shown on here, you would go with the tertiary. If you have a primary and a tertiary, you're going to go with the tertiary. Cool? That's the answer, okay? Again, sterics versus electronics, and the only time that electronics comes into play is when you have a tertiary carbon. Bada boom, bada bing. All right? Give me a thumbs up if you follow me on that. Sean, thanks, Kylie. Thanks, Sean. Good, David. Did anybody, I'm not going to ask. I was going to ask if anybody read this. I told you to read it, but I hope you all did. All right, we got one more slide before we're going to look at some practice problems. But look, under acidic conditions, it's still an SN2 reaction, and you're still going to get inversion of configuration, regardless of which carbon of the epoxide is attacked, okay? Here we have, look, let's draw it out here in detail. Here we have a tertiary carbon, right? This carbon is attached to 1, 2, 3 carbons, so that's tertiary. Here we have a secondary carbon. We've got an acid and a weak nucleophile. So we're going to protonate it, right? We're going to end up with this. I'm probably going into too much detail, but whatever. It's the land of the free for a couple more weeks. Next month, I'm going to have 5 years in America. Crazy. Okay. So you're going to end up forming this intermediate, okay? And then when the alcohol comes in and attacks at the more hindered carbon, right, based on what? Electronic effects, it's going to attack, and it's going to do a backside attack, okay, underneath the methyl group, right? And the methyl group, right, is going to get inverted. It's going to go from being a dash to a wedge like that. Okay, so you get inversion of configuration, okay, based on backside attack. And we could even write that in here. Backside attack. All right, there we go. Sound good? Give me a thumbs up if you follow me on that. If so, we can start looking at some tasty, tasty practice problems. Bum, 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 bum. Anyone? All right, Yvonne, thank you. Great. Yvonne always comes to class. Good. All right. Great. I know you all come to class. I know. Let's see here. David, great. Wonderful. Wunderbar. Let's see here. For each of the following reactions, predict the product and draw a mechanism. Oh, no. I'm kidding. Let's do it. What do we got here in the first one? I'll just ask you. We got sodium methyl sulfide. Is this a strong nucleophile or is this a weak nucleophile? It's actually sodium methylphthalate, but whatever. Is this a strong or a weak nucleophile? If I draw, maybe I can help you out by drawing the Lewis structure. Strong or weak, people? Anybody?
Weak.
Remember, strong is when it has a charge.
Oh.
Right? This is a strong nucleophile, right? So we have a strong nucleophile. For the only time we have to worry about that whole, tertiary electronic effect, that's when we have a weak nucleophile. So since we have a strong nucleophile, we're just going to go for the least hindered carbon, right? So we draw our curved arrow like this. There's our least hindered carbon. We're going to open up the ring. And what would we end up with? Let's draw the intermediate. I'm going to label these carbons. This isn't for nomenclature purposes. This is for instructional purposes only. I'm going to number these carbons 1 and 2 like that, just to help you out, okay? So I'm going to have carbons 1 and 2. I could even label them 1, 2. What else am I going to have? I'm going to have my oxygen, my oxide, like that. I'm going to have my methyl group. Okay, I didn't attack that stereocenter, so its configuration remains. And then down here, I'm going to have my sulfide. This is now a methyl sulfide, like that. And then in the next step is the proton transfer. We could even draw that out, cha-cha, like that. Okay, we do proton transfer. And then we end up with this beautiful product, this alcohol. Put our methyl group here, like this. We have our sulfur and our methyl, and there's the final product. All right. All right. Let's try the next one. We got lithium aluminum hydride. Would that be a strong or a weak nucleophile? Yeah, absolutely. Now, we could draw the mechanism drawing the whole aluminum hydride thing out like this. Okay. Like that, okay? And then we're going to have a nucleophilic attack by our hydride like this, okay? The ring opening like that. And then I'm going to draw the product after both steps because I'm too lazy to draw the intermediate this time. So all organic chemists love shorthand. So we'll draw what we get after protonation. And then all we have here is a hydrogen like that. So we're just going to leave that out. I have a question for you. Cha, there we go. Is this a chiral molecule? No, this is achiral. Okay, this is achiral. So we actually, it's just isopropanol, right? Just isopropyl alcohol is what you end up with in this case. And let's try the last one. I have sodium ethoxide, right? That's a strong nucleophile. We could draw the Lewis structure. I'll just draw the ethoxide. I'm not even going to write sodium. That's really getting lazy, but whatevs. Anyhow, we're going to attack the least hindered carbon like that. Remember, this is carbons 1 and 2. We'll start by drawing those out. Carbons 1 and 2 like that. Okay. We didn't affect this stereocenter over here. We didn't even touch it, so we still have our phenyl here. We still have our ethyl group down there like that. We've got our oxygen up here. I'm going to draw the product of the after the protonation occurs, and then down here I have O ether like that, so I've made an ether. No, these would not polymerize into long chains. No. Because you would be doing the reaction in a solution. So these are done in solution, so there wouldn't be concentrated enough for it to polymerize. All right. Also, I went ahead and determined the stereochemistry of these, chiral centers. So here we have S, and here we have, son of a gun. I bet you that's all deleted now, isn't it? Yep. Yeah, I don't know why it does that. Anyhow, I spent all that time drawing the products, but the product of both of these is S and S. I need to call Steve Jobs. All right, and ask him about my iPad. All right, let's try 13.18. Let's see here. For each reaction, predict the product and draw a mechanism for its formation. So the first step is going to be protonation. So I'll draw my hydronium like this. Okay. I'll put in my lone pairs over here like this. So I protonate. So let's draw what the product is after protonation. I have this protonated epoxide with a positive charge. I've got my methyl group over here. Got this other stereocenter here. Like that. Now if I analyze these two, here I have a tertiary carbon, and here I have a secondary carbon like that. So it's going to attack, right, the water, which is my weak nucleophile, H2O, right, Cha, okay? The water is going to attack what? It's going to attack the tertiary carbon based on electronic effects, and we're going to flip that stereocenter, right? We're going to invert that stereocenter, and so it's going to attack from the bottom like this, okay? And so those two groups are going to flip up, okay? you don't switch the dash and the wedge. They're just going to go from being pointing down to pointing up, okay? So let's draw what we would get. We'd have our carbons from our epoxide. We're going to have our hydroxyl over here. We've got this methyl group over here. We don't exchange these two groups. Here they're pointing down like this, right? They're pointing down. Now you're going to have the methyl still on a dash, the ethyl still on a wedge, but now they're pointing up, okay? And then we're going to have our oxonium like this, okay? And then in the last step, water's going to come in and it's going to remove one of those protons to make the alcohol and the proton transfer. I'm not going to draw that step of the mechanism. I'll just write, proton transfer like this, and then we're going to end up with this product. So we have our alcohol, here's our methyl group, we have this methyl group, we have our ethyl group here, and we have our, so we end up with a diol like that. All right, let's try this one here. I'm going to start by doing my proton transfer. If you want a real quick and dirty way of doing it, you just write H+ like that. I wouldn't recommend it, but if you're really, really confident in your mechanisms, you can just write a proton like that. If you were in a job interview and did that, they would accept it. So like that. All right. And we have our methyl group down here like this. We have our 5-membered ring. That's not even a stereocenter, is it? No. Okay. And then where's the nucleophile or methanol going to attack? I'm going to label the two carbons here. I'm going to label this one A and B. Who can tell me where the methanol is going to attack? Will it attack at A or will it attack at B? Yeah. Good. Oh, I'm getting mixed messages here. Okay. Can we get some more votes here? Okay. It's going to attack at A. Okay. Why is it going to attack at A? Remember, this is acid catalyzed ring opening. That's the whole point of this, is all acid catalyzed ring opening. Acid catalyzed ring opening. So A is tertiary, right? This is tertiary. This is secondary. It's going to attack the tertiary because it's more comfortable with the delta plus, right? Based on the whole bond weakening thing. So I'm going to delete some of this spinach so I can draw a nice clean mechanism here. We'll delete that, delete that. So now my methanol is going to come in as a nucleophile, and it's going to do a nucleophilic attack here. Then I'm going to pop that ring open, and what do I end up with? I'm going to end up with my methyl group pointing down like this, my hydroxyl like this. Remember, this group is pointing down like this, so now it's going to be pointing up. It's not, again, it's not even a stereocenter, but it's going to be pointing up like this. And then I'm going to have my oxonium here like that. And then after the last proton transfer, I end up with the product. Let me see if I can make this easy on myself here. Look at that. Boom. Copy. Paste. Here we go. Now that is how you do it. Just like that. There we go. Cha-cha. All right. There we go. Give me a thumbs up if that clears it up a little bit. The electronic effects. All right, great. So if we go back to the last problem, okay, I know it all got deleted, but here, strong, we could write here, strong nucleophiles do not require acid, right? Do you see any acid in here? I don't, okay? So that just goes to the least hindered side. If we look at this problem, these are all acid catalyzed, okay? So if there's a tertiary carbon, right, like here and here, that's where it's going to go for when you're doing it in acid. That's the whole you know, separating it. Okay. Now, I wrote here in my slides, I say a lot of things that aren't true, right? No, I'm kidding. Anyhow, I said that we would skip the part about thiols and sulfides, but seeing that it's only 8:52, I just want to throw some things out here to you because I don't think it's right for somebody to go through organic chemistry and you to come out and be like, hey, do you know anything about sulfur? What, sulfur? That didn't come up. No, you should know a little bit about sulfur, okay? Let me just tell you a couple quick little tidbits, okay? The first thing is you got to know what a thiol is, okay? A thiol, if you've ever smelled a skunk or, you know, bad smells like skunk smells, like crap, I shouldn't say that, but anyhow, that's the smell largely of thiols, okay? So a thiol is just the sulfur analog of an alcohol. Another old word for a thiol is a mercaptan. If you're like, what, the captain of a boat? No, it's got nothing to do with that. If you're wondering where the word mercaptan comes from, it's because sulfur binds readily to mercury, right? So mercaptan, like it captures mercury. Mercaptan is a super duper old way of describing a thiol or naming a thiol, but I tell you what, it's still used. And in the book, he even says, old habits die hard. Another thing, I know that you all know what an alkoxide is by now. You've seen them like 1,000 times. So if we have this is called an alkoxide, okay? If you have the sulfur analog of an alkoxide, that's called a thiolate, or it can be called a mercaptide, okay? What else? You guys know the name of this. Everybody knows that. You've seen it Avogadro's number of times since you started studying chemistry. That's a hydroxyl. This is called a sulfhydryl. Sulfhydryl, like that. What else? Other things about thiols. Did anybody read the part about thiols in the book? I'm just curious. Anybody at all? I'll back up. No? Okay. So one thing about the whole thiol thing, normally if you work in an organic chemistry lab, they'll have big rooms, you know, where they store all their chemicals. And thiols are always kept in a blue cabinet. I don't know why, if it's some kind of law or something, but they're always stored in a blue cabinet. This is thiols, okay? And people will do anything they can to avoid opening the thiols cabinet because they are so smelly and it has like, you know, ventilation coming out of it or whatever with the negative pressure, you know. Anyhow, and a couple things about working with thiols, I would say that if you're a researcher and you're trying to get graduate students and you do a lot of thiol research, sometimes, I'm not kidding, you might think I'm being facetious, but it's actually difficult for professors to recruit students to work with thiols because it just gets in everything. It'll get in your clothes, your skin. It'll just kind of permeate you and you become kind of like a smelly person and it's nothing you can do about it. So I worked with thiols for maybe 3 weeks in graduate school, and eventually I just couldn't hack it anymore. You know, it was like always smelled bad. Anyhow, just something to think about. All right, you can read the rest about thiols if you want, but I guess I'll skip it if it's not in the ACS final. So this brings us to the very end of the chapter. You've learned all the reactions that you have to know for the quiz. In section 13.12, we'll do as much as we can here. But all section 13.12 is about is just different synthesis strategies with epoxides. So let's see here. It says here, epoxides allow for the installation of two functional groups on adjacent carbons, right? That's why I kept helping you out with this whole 1, 2, 1, 2, right? Let's say your nucleophile is a thiolate. Well, then you can make a sulfide and you can make a hydroxyl at the same time. So you can make two functional groups at once. And notice it says here, whenever you see two adjacent functional groups, like here you have a nitrile and a hydroxyl, you should think of an epoxide, okay? That's where you might want to start, all right? So if you think about what's going on in this reaction here, first, you know, you look at it, it might look intimidating. You're like, what, MCPBA and then sodium cyanide? You get all this? Well, hold on. Let's see the whole show before we make any harsh judgments, right? What you're doing in this first step is you are, you're making an epoxide like this. That's a pretty crappy drawing of an epoxide, but it gets the point across. And then what's happening in the next step? Cyanide is coming in as a nucleophile. Cyanide is a strong nucleophile, so it's going to attack the least hindered carbon like that. You're going to pop that open, and it's going to give you this compound. Okay, so nothing really mind-boggling. It's more a matter of getting used to looking at these pieces and understand what the heck's going on. Let me show you another cool reaction that you can do. What if you take an epoxide and you treat it with a Grignard reagent, right? Then you can make new carbon-carbon bonds. You're like, hey, didn't you say something about a Nobel Prize if you could make carbon-carbon bonds? Yes, if you can find ways to make carbon-carbon bonds, you will be popular in the organic chemistry world. Let's look at what's going on in this reaction. In the first step, we take this alkyl halide, right? Alkyl halide, because bromine is a halogen. We're going to treat that with magnesium, right? David loves to have a solvent, so we'll put diethyl ether in there. We're going to put RMGBr like that. Now, what did I tell you about a Grignard? You can treat it as if this is a carbanion, right? And then what's that going to do? When you treat it with an epoxide, that's a strong nucleophile, strong nucleophile, and that's going to come in and attack the epoxide and crack it open like this. You're going to end up with two carbons, right? Your 2 carbons from your epoxide, and then your alkoxide. Look, last step is just a proton transfer like that. That's a pretty nifty reaction, okay? Very, very nifty reaction. Adding carbons to a chain, good gravy. Good gravy. If you want to be like, held up on people's shoulders and then like chant your name, at an organic chemistry conference, which I know it's probably a life goal of each one of you. Find a way to make carbon-carbon bonds. You will be very popular, okay? An epoxide yields a longer chain with a functional group on the second carbon, okay? What if you had a carbonyl? Can you do something cool with a carbonyl? Hell yeah. Okay, what if you had a carbonyl? Says if you want to put a functional group on the first carbon instead of the second carbon, well, looky, what's going on here, right? If we have RMGBr, okay, like that, again, we can think of that as negatively charged. That's a strong nucleophile. What the heck is going on here, man? Look, let me draw. I'm getting overly excited about this reaction, but this is very cool chemistry, people, right? Cha-cha, we get our nucleophilic attack like this, okay? Then we have our R. Look, this is the first carbon. This is the second carbon. First carbon, second carbon. Then we do a proton transfer. Is this not, give me I won't do that, but this is beautiful chemistry. Okay, very exciting. This is where the class gets, really beautiful and a little more elegant in terms of our syntheses. What else? Well, with that in mind, let's guess I'm throwing us right in it here. Consider the reagents that you might use to make this, okay? This is your first synthesis where you use an epoxide. Now, I got some students who love to ask me the question, like, can I assume that I have any epoxide? Yeah, basically, yes. Assume that you can have you got whatever epoxide you want, okay? Now, look, how many carbons are we adding here? I'm going to have to walk you through this question. I'm adding a total of 1, 2, 3 carbons. And look, I have a functional group on the second carbon. Hey, maybe that might be something I could use in epoxide, right? Okay, what would the epoxide be? Well, I'm going to try to help you out here and think of the arrows going backwards, right? What if now don't draw this, but if I went backwards with my arrows, okay, and did something like this, let me fix that last one maybe. Okay, if I did that, then I could think about, what if I had this? If I had this nucleophile, and if I had this electrophile, look at that. Where would I get those two things? Hey, this looks like I could get that from a Grignard, and this is just 1-methyloxyring, right? This is just 1-methyloxyring. I sound like Bob Ross here. So excited about this. So could we do that? Does anybody have an idea of what my first reagent would be? Where would I start? I like it. Sean just says Grignard. All right, there's a lot of power in that name. He's been dead for a long time, but boy, his name still yields some clout in the organic chemistry world. We'll put magnesium. We'll even throw in diethyl ether as a solvent, and we'll make phenyl magnesium bromide. So, or you can call that, sometimes people call that phenyl Grignard. There we go. So phenyl magnesium bromide. Then what are we going to do? We're going to treat it with that oxirane that I drew right here. Okay, so let me just redraw it. It's just 1-methyl oxirane. Okay, remember, this is a strong nucleophile. It's going to charge. So it's going to do a nucleophilic attack on the least hindered carbon like that. I'm going to draw the intermediate because I'm the instructor and I like to draw intermediates for my students. You're going to end up with this. Look, 1, 2 carbons. On the first carbon, you're going to have the alkoxide. Okay. Nope, shit. Did I draw something wrong here? No, sorry, I'm right. Mr. Dion's losing it. I put my oxygen on the wrong carbon. There we go. All right, sorry. Anyhow, maybe I'll help myself. 1, 2. There we go. 1, 2. So on the second carbon, I'm going to have a hydroxyl, right? The alkoxide is going to be going down here. And on carbon 2, I also have a methyl group. Okay. So then in the last step, I just treat that with water. Done. So overall, this is what? First step, magnesium and diethyl ether. If you want to write just magnesium, I'd accept that. Okay. Step 2 is to treat it with this octane. Step 3 is H2O. Give me a thumbs up if you follow me on that. Like, I think I could do that. Thanks, Andrew. Thanks, Sean. Good. Caitlin. Great. All right. Choo-la-choo. Here we go. Who else? David, Andrew, Yvonne. Great. Great. Well, we got time. It's 9:04. We've got half an hour. This is just the answer to that problem. Well, let's give this one the old college try here. Let's do the first one kind of quickly because I want to spend more time on the second one. The second one's even more cool. I'll just throw it out there to my students. Does anybody have an idea for the first step in the first one? In this one right here? First step. I like the way you think, Andrew. Yeah, MCPBA. I'll buy that. Come on, erase. Okay, so first step, we're gonna take that alkene. Let me just adjust my screen here. Oops, come on. There we go. First step is we're gonna take that alkene. Yeah, and we're gonna treat that with MCPBA, and we're gonna make an epoxide. Okay, so I don't care how you draw it. This isn't a stereocenter anyway. Like this, you're gonna end up with that epoxide. Okay, then what are we gonna do? Who could help me out with the next step? If I want to make a nitrile, what would I use as a nucleophile? I'll give you a clue. Ends with iodine. That's right, Diego. Sodium cyanide. Yes. So you'd use sodium cyanide. I'll draw a little bit of the Lewis structure here. So it's going to attack at the least hindered carbon, right? Based on sterics only. You would end up with this. I'll draw the intermediate. So like this, like that, like that. This methyl, doesn't matter where it is. I'll draw it the way they have it. Like that. And then in the last step, we throw water on it and we end up with our product. And so overall in this reaction, first step is MCPBA. If you want to write peroxyacetic acid, right, if you were to write this, that works too. Same thing, right? Or MCPBA. Second step, sodium cyanide. Third step, water. All right, I'm going to just delete this. Okay. And I want to spend some time on this next problem. Okay, you ready for the next question? What would I do if I start with cyclopentane? And I'm in organic chemistry 3111. What are my options? And Sean, don't give me or who is it? Yeah, Sean, don't give me the funny option. Give me the real option. Right. Okay. Don't say burn it. Good. So the first step is we're going to treat this with just bromine and light. We're going to brominate it, right? So that's all we've got. And the first step is to treat this with bromine, and we end up with bromocyclopentane like this. Well, look, if we're making a trans diol, I'm going to back up a little bit. That means retrosynthetically, we would want to make that from an alkene, right? And then we can treat that with MCPBA and then finally with acid. All right, so how would we make an alkene from this, bromocyclopentane? I would just treat it with DBU, DBN. You could treat it with sodium methoxide. I'll use sodium methoxide because it's the most popular one with my students. And then you'd make cyclopentene. Next step is to treat it with MCPBA or peroxyacetic acid. Either one works. Just writing out MCPBA is easier, I guess. There we go. Cha. We end up with our epoxide like that. And then to make this product, we just crack it open with acid. So overall, the first step is bromine and light. The second step is sodium methoxide or DBU would work. The third step is to treat it with MCPBA, and the last step is to treat it with H3O plus to break that open and make a trans diol like that. All right, boom. Who thinks they could do those? All right, in the interest of time, I'm going to kind of stop there. You have the answers to the solutions to these ones. These are just more synthesis problems. Maybe we'll do the first one. Let's do the first one quickly. This one I'm going to do using a Grignard as well, and I want to add 2 carbons. And so retrosynthetically, I would think of using this as, this is called acetaldehyde. It's an aldehyde. So in the first step, I would take this bromocyclohexane, and I would treat it with magnesium and diethyl ether to make cyclohexyl Grignard. I'll draw it out like this. Okay, and then in the next step, you would treat it with that aldehyde like this, and then I'll draw the curved arrow. You would do a nucleophilic attack like this, and you would end up with this compound. We have the charge here, right? Oops, like that. And then in the next step, you treat that with water to get the product. So overall, this first step is magnesium and diethyl ether. The second step is to treat it with this aldehyde. You don't have to know the name of the aldehyde, of course. And then the last step is to treat it with water. All right. So there we have it. We have 5 minutes left, so I just want to talk about the quiz. Do you guys want to know what's on the quiz? I can give you my list. Okay. All right. Somebody says yes, please. Okay, I'll make a laundry list right here for you. Okay. You saw it here first. You need to know what an ether is. Okay. So you need to be able to recognize an ether as a functional group. Functional group. You need to know IUPAC and common names of ethers. You need to know about acidic cleavage of ethers, and we went over that last class. You need to know a little bit about intermolecular forces. Remember, I spent some time talking about how an ether has a dipole and London forces, and an alcohol has hydrogen bonding, and a dipole and London forces, and an alkane only has London forces, right? What else? You need to know a little bit about bond angles. I had a whole slide in there about the bond angles on ethers. The bigger the group, the more they get pushed away. What else? In terms of ether synthesis, okay? Ether synthesis, you need to know Williamson, ether synthesis. You also need to know the acid catalyzed ether synthesis, so acid catalyzed, which I told you is only good for making symmetrical ethers, but I could ask you about the acid catalyzed synthesis of a symmetrical ether. Sure, we've covered it. You need to know about epoxides, how to make an epoxide, and we learned 2 ways to do that, using MCPBA or making a halohydrin and then treating it with sodium hydroxide. So we went over those. So epoxide formation or epoxide synthesis, whatever you want to call it, you need to know those. And you need to know that the alkoxy, the oxygen of the alkoxide and the bromine of the leaving group, or the bromine, have to be anti-periplanar. So anti-periplanar, as we say in French. What else? You need to know about halohydrins, of course. Halohydrin formation. I think I even put a question on there about making a halohydrin, right, which is using bromine and water together. That's a halohydrin. Epoxide opening. We spent a lot of time talking about that today. I'll write it over here. Epoxide opening. So with either a strong nucleophile or acid catalyzed, both ways that we went over in gross and gory detail today. And what else? Oh, you need to know about alkoxy mercuration, demercuration. So alkoxy mercuration, demercuration, because we looked at that, right? Using mercuric acid, right? Step 1 is mercuric acetate and an alcohol, and second step is sodium borohydride. Okay, so those are the things that you have to know that are all covered on this quiz. 20 multiple choice questions, not a long quiz. Okay, again, I will open it for a little bit longer, and I will post an announcement about that. Not right away because I have class in 10 minutes, but I'll do it this afternoon for sure. All right. Well, it's 9:14, and there we go.